All right, so for our unit 4 exam here, okay, so global systems unit exam. Obviously, it's a pretty short unit. Okay, it only took us a couple of weeks to get through it, okay, and there's not a lot there. But that means, though, it's just as, I mean, it's going to feel shorter than the others, but it's still got as many kind of questions and stuff on it as your other ones have. So you need to know the material, which there's less of, a little better. Okay, so the types of questions that will be on there are what we're going to talk about. Okay, but first, let's look at what kind of things are going to be on here, period, in terms of topics. All right, the very first thing we talked about was climate. Okay, that was the first day. We talked about climate from two perspectives. We talked about the components of climate, which are temperature, precipitation, light, and wind. Now, the way that that's going to be tested is it's going to work in conjunction with the other part of climate, which is the factors that affect climate, okay? And that would be things like latitude, which was the most important climate factor, altitude, which was basically the second most important, okay? Mountain barriers, proximity to oceans, centers of high and low pressure, okay? All those other things that we talked about. Okay, now there could be a couple of multiple choice questions about, components and factors and things like that. But the biggest place where this is going to get tested is in the written response. And the question is going to work like this. I'm going to give you a picture of Canada, and I am going to point to a spot in Canada. And I am going to ask you to describe the climate of that location and then explain to me why you think it is the way it is based on the factors that would affect that place. Okay, this is part of the reason we did that climatogram activity, okay, is so that you would have a look at some of the kind of areas of Canada and have some familiarity with it. So I would say it might not be a bad idea to review what you wrote down for your climate groups in the climatogram activity in order to kind of help you with this question. It's going to be, a pretty obvious city. It's going to be, going to have pretty obvious factors. I want to know if you can put those together. Okay, so that's how I'm going to ask about that one. So you'll be told, here's a city in Canada, and I'll show you where in Canada it is in case you didn't know. Okay, and then you'll have to go from there. The climate will be like this, okay? So if it was Okotoks, then we would say, okay, well, the climate is going to be as follows. Temperature will vary throughout the year. There will be cold winters and warm summers. Light will vary throughout the year because of the tilt of the earth, okay? So there'll be more direct sunshine with longer days during the summer and the opposite during the winter, okay? Precipitation is going to be variable. It'll come in all forms, snow, rain, okay? Hail, whatever, with the wettest months being kind of like, June, July, okay, something like that. Okay, and then the factors that affect that, the reason Okotoks climate is the way it is because it is a high latitude area. Okay, it's quite far from the equator, so there's definite seasons. Okay, it's reasonably high altitude. We're over 1,000 meters here, okay, above sea level. And so that can make it a little bit cooler, and we are not close to any oceans, and we have a set of mountain barriers that severely affect the types of winds and weather that is received in this area. Something like that. Does that kind of make sense for what I'd be expecting? All right, second thing that we went over is climatograms, okay? And we talked about that just on Friday when I was finishing up all the biome stuff. So the expectation there will be, I give you a climatogram, and you tell me, what does the climatogram say? Okay, so first, you can look at it and go, well, that says the temperature does not fluctuate on this climatogram, therefore it must be near the equator. Precipitation is, even all year long, so that must mean that this is a fairly wet place. So this is likely to be a tropical rainforest because tropical rainforests are warm, wet, or only located near the equator. Explain kind of thing. Okay. All right, so that'll be a written response question. Okay, and then we talked about energy transfers in global systems. This is actually one of the bigger lessons in terms of the stuff that's on it having connections to everything else in the unit. So there's going to be several written response items asking you to apply your knowledge of heat transfer based on this lesson. All right, so when we talked about energy transfers in global systems, okay, the first thing we said was that the three fates for light when it strikes the Earth's surface is that it could be absorbed. If it's absorbed, then there'll be a change in temperature. It could be used or converted by photosynthesis, meaning there's got to be plants around. And it could be reflected. Okay, and these two things, how much of them happens, is affected by that. Okay, so albedo is the reflectivity of the Earth's surface at that location. Okay, if it's, summertime, then obviously the albedo is much, much lower. Plants are green, absorbing lots of solar energy, converting it by photosynthesis. Okay, soil is exposed, darker colors are available, things like that. In the wintertime, the exact opposite. Plants are dormant, there's no photosynthesis going on. Snow is covering the ground, the albedo is very high. Okay, everyone following me there? Okay, so there will be a written response question just about these three things. Okay, I will show you a picture of a place, okay, and describe a place, and you will have to tell me what happens to the light in that place and give me some idea about how much of each one of those things is going on in that particular situation. Okay, keep in mind that the location I'm going to show you is a natural location. Okay, I don't want anyone talking about solar panels when they answer this question. Okay, this is the natural state of things that we're talking about. Everyone follow? Okay, because it says convert by photosynthesis, absorb or reflected. It doesn't say I'm powering my house because I live in Drake. Okay, right? That's not what we're doing here. All right, so written response question about what can happen to light when it strikes the Earth's surface. Okay, then the layers of the Earth here and how they play a role in energy transfer. So looking at the atmosphere, the lithosphere, okay, and the hydrosphere, right? Probably mostly multiple choice questions about those two things, right? But obviously we need to understand that the reason the atmosphere is most important for transferring solar energy is because it is the most fluid part. It touches all parts of the Earth. It can flow the easiest, okay? That's where wind occurs, and wind is an example of convection, okay? One of the three methods of heat transfer. Okay? Remember that the atmosphere and the hydrosphere interact through the water cycle, helping latent heat to be available as part of the energy transfer system on Earth. Okay? Water vapor moving from one place on Earth to another. Okay, and then we said the lithosphere is mostly involved with absorbing. Okay, it's affected by albedo, but it only transfers energy by conduction, which means it's not going very far or very fast. Okay, now there will be a question that's going to ask you to apply your knowledge of energy transfer, energy absorption, and things like that. It'll be a practical application question that'll be somewhere along the lines of this. Okay, I'm going to present you with a challenge. Okay, that would be like either I want you to find a way to heat something up, or I want you to find a way to keep something cold or keep it warm or something like that. And in other words, I want you to think about how can I get heat transfer to work for me, or how can I get heat transfer to stop so that I can keep this thing the way it already is. All right, so what I mean by that is you've got to talk to me about how you're going to design something to stop or harness convection, conduction, and radiation. All right, so an example could be, let's say that I want to keep food cold in a building that's out in the middle of the desert. Okay, so things I would want to make sure of if I wanted to keep something cold in the desert would be that the building it's in should be what color? White. Okay, so right there you're telling me I know that the building should be white because white reflects all the, or as much radiation as possible. So you've just told me radiation is a way that energy can get in. Here's how I'm going to stop it. Okay, and then you'd probably want to talk about how you're going to insulate the walls. Okay, we need to insulate the walls because insulation will stop convection from happening. I think we didn't talk about that a whole lot, so I'm just going to kind of go over that again here. Okay, so with convection, the big thing with convection is that convection happens when air is allowed to circulate. Okay, hot air rises, cool air descends. As long as air can circulate, convection can happen. There's two ways to stop convection from happening. Make it difficult for air to move or to remove the air entirely. All right. With insulation, how many people have seen like the fiberglass, the pink stuff that goes in houses? Okay, so insulation, fiberglass insulation is small glass fibers, okay, like really, really small. That's why you have to wear a mask and gloves when you put it in, because if you inhale it, it gets in your lungs really bad, okay? So these glass fibers, they're just kind of intertwined all together. Trapped between them is air. Can that air move? No. If the air can't move, convection can't happen. That's why we fill our walls with it. Okay, so if I've got, okay, here's a wall, okay, here's the inside of my house, here's the outside of my house, okay, very, very cold outside. If my walls are just hollow, then the second law of thermodynamics is going to work against me, and this hot wall is going to want to transfer energy to this cold wall, okay, and all that's going to happen is hot air will rise, okay, cool air will move in to replace it, and I will get a convection current happening inside my wall that will steal energy away from my house. Okay, everyone follow me there? Right, so that's what insulation does. It keeps that from happening. The thicker the insulation is, the better off you will be. All right, you guys probably don't have any trouble with that. Okay, most modern homes are well insulated. I owned a house in Lloydminster that was built in the late 30s, early 40s, and if I went to, there was one night where I went to sleep with my hair wet, and I woke up frozen to the wall. Okay, like the wall was so cold that I actually froze to the wall. Okay, I woke up in the morning, it was really bad. Well, yes, to some extent, not necessarily in that much detail, but you would tell me insulation will prevent convection by preventing the movement of air, right? That means, yeah, something like that. Okay. The other way to prevent convection is to remove air entirely. If there's no material there to flow, then convection can't happen. So we could create a vacuum also, and that's what we typically do with windows. We can't put fiberglass insulation in between two panes of glass so you can't see out. So what we do instead is we have two panes of glass in a window, or even three, and then we have a vacuum between them. So we actually physically suck all the air out of there and then seal it tight. With no air in between the panes, the only way for heat to escape would be through radiation through the window. All right, but convection and conduction can't occur if there are no particles to transfer the heat with. Everyone follow me on that? Okay, so if you have like these, like the thermos mugs, okay, like this one here, okay, they're, the metal ones, there's a vacuum, they suck all the air out between the inside vessel and the outside vessel, okay, and that keeps the heat from escaping through convection. Everyone with me on that one? Okay, like the big Yeti cups, they do the same thing. All right. Yeah, so you would have to basically explain to me how would your structure work, or your device, or whatever it happens to be, or maybe I even give you the structure or device and you have to explain to me why it would work. Okay, like we talked about quinsies the other day as well. Okay, how if you hollow out the pile of snow, okay, there's all these dead air spaces because snow, is the flakes, and there's all this air trapped in the snow. It's a very good insulator. Snow is white. It reflects your energy back to you. Okay, so you've got radiation working for you. You've got convection not taking away any heat. Okay, conduction's not taking away any heat either. Okay, things like that. Does that sort of make sense? Okay, so kind of an apply your knowledge type of question on heat transfer in the written response. So definitely talk about conduction, convection, and radiation in that question. Okay, and then we talked about wind patterns. Okay, so there'll be a couple of multiple choice questions on wind patterns, and then there's going to be a couple of questions on wind patterns in the in the written response. Okay, so there'll be one about prevailing winds, and there will be one question that asks strictly about how does energy get from the equator, where the bulk of the solar energy is received, to more northerly parts of the world. Talk about the mechanisms by which that happens. Okay, the mechanisms by which that happens. Okay, convection, obviously the biggest one. Okay, the jet stream, another big one, that high altitude wind that we talked about. Okay, and latent heat. I think I have that written. No, I don't have it written anywhere. Okay, and latent heat. Okay, those are the mechanisms. So make sure you talk about each one. Okay, you're going to list the three and then tell me, okay, so convection works this way, right? When we were talking about it on Earth, or when we were talking about it in class here, okay, we said, okay, a hot air rises, okay, cool air descends to replace it, okay, and that happens all the way up to the pole. That's convection, that's moving air, okay, from one place to another. And then sometimes that can be carried, or latent heat can be carried by that. Sometimes the jet stream can move latent heat around, okay, push air masses in areas of high and low pressure, okay, all of that kind of stuff. That's all wind patterns and energy transfer on Earth. Okay, and then there will be a question about prevailing winds. Okay, prevailing winds, okay, are convection plus the Coriolis effect, right? So as this happens here, as the convection happens here, okay, the Earth spins this direction underneath it, okay? So that air, this air here that's moving downwards gets deflected and makes it seem like it's coming from the east instead of from the north, right? And similar thing happens where we are, okay? The air is moving northwards, but it gets deflected by the rotation towards the east, so we feel it coming from the west, etc. Right? Be able to explain how convection and the Coriolis effect work together to create patterns of prevailing winds. That'll be another written response question. Okay, questions so far? All right, after we talked about that, we talked about specific heat capacity. All right, remember that specific heat capacity is why proximity to oceans is a factor that affects climate. Water has a very, very high heat capacity. And so it can gain or lose lots of energy without changing its temperature very much. And that enables it to regulate the air temperature near it, which is why Victoria, which is, or is basically the same latitude we are, is so much warmer than we are. Okay, it's closer to the ocean. The ocean can regulate temperature because it's made of water, which has a very high specific heat capacity. Okay, so there could be, some multiple choice stuff, maybe about that. Okay, and then there'll be a written response question asking you to do an E equals MC delta T calculation. All right, not difficult. That should be a pretty easy set of marks there. All right, and then there will be a latent heat problem. Okay, we did a bunch of those. It wasn't something you guys had any trouble with. Okay, just know that there'll be a heating curve of water question. So draw the heating curve of water, identify your starting and ending points, okay, calculate the amount of energy for each step, add them together, okay, give me your final answer. Okay, the one on your test, I'm pretty sure I made 3 steps. Okay, questions there? Okay, and then the last thing we talked about was biomes. Okay, so we've already talked about how biomes is going to be connected to the climatogram, okay, in the written response, but there will be a number of multiple choice questions where you will have to identify what biome is being talked about in that particular question. Each biome question contains a description of the biome as well as a picture of the biome. Caution, don't just rely on the picture. Okay, read the description as well. I mean, most of the time when you look at the picture, yeah, you'll probably have the right one in your mind. But, okay, I did show you a picture when we were talking about the prairie biome that looked very much like a desert, right? And we don't want to just go, oh, that looks like a desert, pick desert. Okay, make sure you read the description. I will have key identifying points in the description, okay, about that biome. So make sure you read the description as well. Okay. That's it. That's what's on the test. Okay, so for a lot of those written response questions, remember, level of detail is going to be important. Okay, make sure you include key things, explain them well. Okay, those key points. Okay, explain them well, tie them together. Right, the multiple choice part, I don't think is going to give you too much trouble. Okay, there's a few in the multiple choice. There's a few questions about energy transfer and albedo and things like that, but nothing like too terrible tricky. Okay, on that. Okay, that's what's going to be on there. Okay. All right, so there are 25 multiple choice questions. Okay, front page of the exam has your formulas on it. So it's got E equals MC delta T, E equals MLF, E equals MLV. It's got specific heat capacities on there that you will need for the test. Obviously not all the specific heat capacities that are on your sheet, but the ones you'll need for the test. Okay, and then, like I say, there's multiple choice questions. They are talking about, soil layers. I forgot to review that. Soil layers is going to be one as well. Okay, so like A, B, and C horizons. And then there's stuff on, lithosphere, hydrosphere, atmosphere, okay, biomes, climate, the water cycle. Okay, I mentioned the water cycle, but I forgot to go into it in detail. Okay, please make sure that you can identify the parts of the water cycle. Right? If I give you a diagram of the water cycle, you got to be able to tell me evaporation, transpiration, runoff, infiltration, okay, precipitation, okay, all of that kind of stuff. Make sure you can identify those, okay, from the diagram, right? So we get those right. And then there's some stuff again on a little bit of stuff on biome, a little bit of stuff on factors affecting climate again, some stuff on energy transfer and albedo, parts of the earth. Again, what happens to light when it strikes the Earth's surface is in there. Energy transfer, latent heat, energy transfer, energy transfer, energy transfer. You catching the theme here? A lot of energy transfer stuff in the multiple choice. Okay. Some more latent heat stuff, albedo, functions of the atmosphere, functions of the hydrosphere. Yeah, okay, and then like I said, we got the climatogram question in the written response. We've got a question about a location in Canada describing climate and factors that affect it. Okay, global wind patterns, prevailing winds, location where you're talking about what happens to light when it strikes the Earth's surface. Okay, an energy transfer application question, a specific heat capacity problem, a latent heat problem, and another energy transfer / latent heat question. Okay, so there's 9 written and 25 multiple choice. So this is the shortest one you've had. Okay, it's out of 71 marks. I think before that your shortest one was like 74 or 75. Okay. All right, questions from you guys? Anything you want me to go over in more detail or show you again? Okay, so when light hits the Earth, okay, that part of the Earth determines, first off, because of its albedo, determines whether or how much light will be reflected, because that's one of the things that can happen. Okay, if it reflects off the Earth, then it's gone. Okay, maybe it gets trapped by the greenhouse effect, comes back again, but for the most part, once it hits and goes off, that's it. We didn't gain anything from the reflection. If the area it hits is darker in color, then that area may absorb some of the light. If it does, the temperature is going to go up because we've absorbed energy. Okay? If that area is covered in plants, then they may convert that incoming energy into chemical energy, starting food chains and things like that through photosynthesis. So that's the three things that can happen. Okay? What you would have to describe in the question on the test is, why is this much being absorbed? Why is there or not photosynthesis going on? How much is being reflected and why? So, okay. Oh, the heating curve? Okay. Okay, so let's say okay, so this will be a three-step question here. Okay, we just want to figure out how much energy is required to heat 800 grams of ice at minus 10 degrees Celsius into water at 50 degrees Celsius. So we always said, first thing we want to do is draw our heating curve and mark on there the starting point and the ending point. So minus 10 would be about right here, and 50 would be here. All right, so that's going to mean there's step 1, there's step 2, and there's step 3. With me so far? Okay, so anywhere where the line is going up, we are changing the temperature of the material, which means we're going to use E equals mc delta T to figure out how much energy is used anywhere the line is diagonal. Okay, anywhere the line is flat, then we're changing the potential energy of it, so we would use either E equals mLF or E equals mLV. Okay, for this one, which one am I going to use? E equals mLF, right? Because it's going from freezing to melting, right? If it's up here, it's vaporization because I'm vaporizing the water, right? Okay, so those are going to be my three steps then. So in step 1, I'm going to use E equals mc delta T because I'm heating the ice from minus 10 to 0, okay? Because that's where this part goes, from minus 10 to 0 degrees Celsius. So that'll be 800 grams times the specific heat capacity of ice, which is 2.116, times the temperature change. I'm going from minus 10 to 0, so my temperature change is only 10 degrees. Oh, not 4.2. 2.116 times 10. All right, so we're looking at 16,928 joules. Okay, so that's step 1. After step 1, I now have ice at 0 degrees Celsius. At 0 degrees Celsius, ice melts. Okay, so now I'm going to be melting the ice. The temperature is not going to change while this is going on, so this is where I will use the latent heat of fusion for water. And that'll just be 800 grams times 333 joules per gram. All right, so we got 266,400 joules. Okay, once I've melted all the ice, now I have liquid water at 0 degrees Celsius. I'm going to warm it up to 50 now. So now I'm changing temperature again. So I'm going back to this formula here for step 3. Okay, so that'll be 800, and now it's water, so I use the specific heat capacity of water now, and I'm changing it from 0 to 50 degrees, so the temperature change is 50. Okay, so 800 times 4.2 times 50, so 168,000. I add all three of those numbers together, I've got my final answer. All right. Okay, what else?
With like prevailing winds, do we need to know like each different level of like the earth, like which way it's going
Yes.
and stuff?
Yeah. So
Or just like that north goes to the right?
I would say that yes, you do need to know what's going on in each of the three levels. So anything moving from north to south is going to be deflected east, from the east. Okay, so at the very top and at the equator, it comes from the east. Where we are, it comes from the west. That's all you have to remember. It's just those three.
And then also, we were talking about like how Chinook only happen in winter, like because of the prevailing winds. Like, so I didn't get that. Cause I was reviewing a podcast and we were talking about that.
Okay, so we see the effects of the Chinooks more in the winter time. It's not that they don't really happen in the summer, but they're not as obvious in the summer because in the summertime we're tilted more towards the sun. So we're getting more incoming solar radiation all the time. And typically the snow cover is gone from the mountains. So the mountains absorb the energy as opposed to steal it from the air as it goes over. Okay, so when the cold air comes over from the Pacific, it's dried out because it's dropped all its precipitation, and now it's cold and dry, and it starts running down the mountains. Okay, as it runs down the mountains, it picks up kinetic energy through the friction between the air and the mountains as gravity pulls it down, and that's what builds up the heat as well as the speed of the winds. Pressure changes can also affect that because as that air comes down, okay, it gets heavier and it builds up atmospheric pressure, very high atmospheric pressure. That's what causes that Chinook arch, right? The Chinook arch is where the high pressure is. That's why there's no clouds there. On the other side, the pressure is much lower, and so you do see clouds, and it's a definite ring, right? Like you guys have all seen the Chinook arch, right? You all know what I'm talking about. Okay, so that's what caused that, is that it creates a massive change in pressure that just doesn't usually set up in the summer because incoming solar radiation is different in the summer. Yeah. Okay, Marty. Okay, so hydrosphere. Okay, hydrosphere is just talking about all the water on Earth. Okay, any water on Earth is part of the hydrosphere. It contributes to the energy transfers on Earth through ocean currents, as well as the fact that, again, water holds a lot of energy. Okay, so it's a factor that can affect climate if you're nearby it, but also it is the source of the water that carries latent heat from one place to another. So the role of the hydrosphere is to get latent heat moving, and then to hold and absorb lots of the solar energy that comes in. Okay, and the lithosphere is just all the rock. So it's the solid parts of the earth. Basically, the most important thing about the lithosphere is it's where the soil is. So it affects the conversion of solar energy into sugars by plants. Without the soil, there'd be no terrestrial photosynthesis. It would all be aquatic photosynthesis. Okay, what else, guys?
When you give us the climatogram to like match with the biome,
Yeah.
you have to like describe the biomes like vegetation and like animals. Like, you're not really need to know.
No, I'm not going to worry too much about vegetation and animals unless it's something that's, important for the description. Like if it was tropical rainforest, you'd say, no, the vegetation is thick and lush, but you wouldn't have to, beyond that, you wouldn't need to say anything. Basically, what I'd be looking for there is, again, first off, describe what the climatogram says. Like, tell me, Mr. Codere, I know how to interpret this climatogram. The shape of the climatogram says the following. And then say, all right, because of this area is likely influenced by the following things, meaning it's probably this biome because this biome structure fits with this for this reason or these reasons. Right? So it'll be a 5-mark question. Like 2 marks will be interpretation of the climatogram, a mark for correctly identifying the biome, and then 2 more marks for explaining why that biome fits. Okay, so like there will be 1 correct answer, okay, for which biome it fits with that's best. Okay, if you have that one and a good explanation for why, then you'll get 5 out of 5. If you pick something that's not as good a fit, okay, but like I read your answer and go, okay, yeah, I could see why maybe they thought that one instead of what's actually the right answer. If your explanation is okay and you still correctly interpreted the climatogram, you can still get some part marks. All right, you could probably get like, depending on which biome you picked, you could get, 3 out of 5 or something like that. Okay, but I mean, if you're just way off, okay, like if I show you something that's got a massive bell curve whose temperature barely ever gets above freezing and there's almost no precipitation, and you tell me it's the tropical rainforest, I'm going to go, no, probably not. And you're probably not going to get very many marks for that. Like, you won't get any. Okay. All right, what else? Okay, I posted in Google Classroom earlier today the review sheet for this unit. Okay, so I would say have a look over that. There's the same kind of things that I'm going to ask on the test are going to be on there. Okay, it looks like this. All right, so we've got a climatogram on there. You'll get a climatogram like this on the test, except it won't have the location on it because obviously that would be then a dead giveaway for what biome it would be in if you knew your geography. Okay, but looking at this one, okay, give me the interpretations. Big things to look at, guys, when you're looking at this climatogram, look at this shape first. If it's got the bell curve, then it's not a tropical climate. Okay, hot desert is out. Tropical rainforest is out. Savanna is out. Okay, none of those fit with a bell curve. Okay, if it has a bell curve, it's something temperate. Okay, something temperate. Then you have to look at where that bell curve is. This bell curve almost never goes, it's got only a couple of months that are barely below zero. Okay, very barely below zero. And it's also not super hot in the summertime. Okay, we're looking, 20 degrees-ish, something like that. And we've got even precipitation all the way across. Those are the things you want to talk about when you're thinking about which biome does this fit with. Okay. All right, so there's other things on here. Describe the major components of climate. Okay, explain why the climate of Okotoks is the way it is. Describing the factors, because obviously you're going to have a question like that, but it won't be Okotoks. Okay, on the test. And then there's some other things here. Okay, just talking about explaining a couple things in your own words about the lithosphere, the atmosphere, the hydrosphere, okay, the water cycle, structure of soil. Okay, there's some solar energy stuff, wind pattern stuff. Okay, another question on biomes. These are all spruce trees, by the way, in this picture, because sometimes it's hard to tell, but they're all spruce trees. Okay, specific heat capacity and the latent heat problem, and then question number 16. Okay, this one you'll have to think about, but I almost always have a question like this, okay, on the unit exam about latent heat and how that can really affect a source or be a source of energy for an area, or really affect the climate if it's lacking, okay, something along those lines. All right, so there's some stuff there for you to look over, okay, in terms of preparing for the unit exam. Okay. All right, so let's have you working on that then, and then hopefully some more questions will come up. If they do, just pop over and ask. Tomorrow, we'll do chemistry review. Okay. Wednesday, we'll do like biology review. And then Friday, I'm just going to quickly go over your test and we'll do physics review. Okay. So I'm spending a bit more time on chemistry and biology because they were longer ago. Physics was quite a bit more recent. But obviously, if you have questions on any unit, okay, on any one of those days, I'll answer them. But my focus will obviously be on those units that day. Okay. So that's the plan going forward for the rest of the week.